right now. The space around Earth is becoming crowded enough to pose real operational risks. Not in the future, not hypothetically, right now.
I'm Jonathan McDowell. I'm an astronomer at the Center for Astrophysics. So space junk is our generic term. The more formal term is orbital debris. And it is any artificial object in space that isn't doing something useful. We have also, unfortunately, space junk from collisions of satellites. And, if you get hit by even a small piece of debris traveling at 17,000 miles an hour, that's really going to hurt.
That statement comes from an astronomer, not a journalist, not a politician. Low Earth orbit is now filled with active satellites, inactive satellites, rocket stages, and debris fragments. All of them move at orbital speed. A collision between two objects can generate thousands of new fragments, each capable of damaging or destroying other satellites. This is not new. Collision probabilities are well understood. Long-term models have existed for years. Companies launching satellites today know the risks. Yet the pace of launches has accelerated. Thousands of satellites have been deployed in just a few years, with tens of thousands more approved. Most are launched by private companies building massive commercial constellations. This matters because modern infrastructure depends on space systems: GPS, communications, weather forecasting, aviation navigation, emergency response, military coordination. Low Earth orbit is limited. Only certain altitude bands are practical, and they are heavily used. So here is the central question. If the risks were known, why did expansion accelerate instead of slow down? Why was congestion managed rather than prevented? And why might the same companies increasing orbital density eventually be paid to reduce it? Quick pause. If you value investigations like this, subscribe, like, and hit the notification bell. It keeps the channel alive, because what comes next suggests this was not accidental. It was strategic. Objects in low Earth orbit travel at roughly 17,000 miles per hour. At that speed, even very small debris can cause catastrophic damage to a satellite. When two objects collide, they typically fragment into many pieces. Each fragment remains in orbit and increases the likelihood of further collisions. This creates what engineers refer to as cascading risk. One collision raises the probability of subsequent collisions. This is not theoretical. It is a direct consequence of orbital mechanics. Before we continue, we want your opinion. Do you see this situation as an unavoidable result of technological progress, or as a risk that companies knowingly accepted because it aligned with their business interests? Satellites are not optional infrastructure. They provide time synchronization for financial systems, enable global navigation, support weather prediction, and carry communications traffic used by civilians and governments alike. When enough satellites fail, the effects extend well beyond space operations. The risk is concentrated in low Earth orbit because it is the most economically useful region. It allows low latency communication, lower launch costs, and easier satellite maintenance. For these same reasons, it is also where congestion grows fastest. This is where large commercial constellations operate. This is where Earth observation systems operate. This is where the International Space Station operates. Statements suggesting that space is vast miss the operational reality. The usable orbital environment is limited, and it is becoming saturated. Importantly, this situation did not emerge unnoticed. Scientific warnings, engineering studies, and agency reports all identified these risks years ago, which leads to a critical question. If the danger was already understood, why did the largest satellite deployment in history proceed anyway? And who benefits when operating safely in orbit becomes increasingly difficult for everyone except the largest players? To answer that, it helps to look at the problem from a strategic rather than a purely technical perspective. Beginning in the late 2010s, the space industry shifted toward large satellite constellations. Instead of deploying a small number of high-cost satellites, companies began deploying thousands of lower-cost units to provide global services. Starlink, Project Kuiper. These systems promise continuous global coverage, but their most important feature is scale. Deploying thousands of satellites creates persistent presence in orbit. It increases operational priority and forces other operators to account for that constellation when planning their own missions. These deployments were not experimental. Companies employed orbital dynamics specialists. They ran long-term simulations. They analyzed how collision risk increases with density. They understood the limitations of low Earth orbit. This was not ignorance. It was a decision to accept known risk in exchange for market dominance. From a business standpoint, the logic is straightforward. Being first and largest creates dependency. Once governments, militaries, and emergency services rely on a private satellite network, that network becomes critical infrastructure. At that point, regulatory pressure changes. Disrupting service has political consequences. Intervention becomes more difficult. Whether orbit remains manageable or becomes more hazardous, the largest operators retain an advantage. They already control fleets, tracking systems, and maneuvering capability. New entrants face higher costs and greater risk. As congestion increases, the central question shifts. Not whether expansion should slow down, but who will be capable of managing the consequences. That shift sets the stage for what comes next. That strategic advantage remained theoretical until a direct competitor with comparable resources emerged. In January 2026, Jeff Bezos' space company, Blue Origin, announced Terawave, a new satellite constellation. 5,408 satellites planned, not for consumers, but for governments, data centers, and enterprise clients. This changes the calculation. Starlink already operates thousands of satellites. Terawave plans to begin launching in late 2027, offering speeds up to 6 terabits per second, far beyond typical consumer capabilities. These are not merely communication satellites. They are infrastructure for the next stage of computing. Both Bezos and Elon Musk have openly discussed moving data centers into orbit to bypass terrestrial energy limits. Whoever controls the orbital backbone influences the future of AI processing. The timing raised eyebrows. In February 2026, Musk abruptly shifted SpaceX's long-standing priority. After decades of emphasizing Mars, he announced plans for a lunar city by 2035. The official explanation was technical sequencing. The unofficial speculation was that Bezos was closing the gap. Days earlier, Bezos posted a black and white image of a tortoise, Blue Origin's mascot, symbolizing its motto, "Slow is smooth, smooth is fast." The message seemed deliberate, patience versus acceleration. Musk publicly dismissed it with humor. Yet SpaceX soon filed regulatory paperwork that analysts say could support up to 1 million compute satellites for orbital data centers. The rivalry, quiet for months, reignited. This time the stakes were not internet coverage. They were control over AI infrastructure in orbit. Track the sequence, Terawave announced. Musk pivots to the moon. The tortoise appears. Orbital compute plans accelerate. Officially, independent business decisions. Unofficially, some analysts ask whether the competition has shifted beyond commerce. Online speculation pushes further. Search for Bezos versus Musk conspiracy, and you will find scenarios that read like science fiction. Some argue Musk's lunar pivot is strategic positioning. The moon lacks atmosphere. In theory, mass drivers could launch material from its surface into orbit using electricity alone. Control the moon, and you control height, ground difficult to contest. Bezos, in this framing, is building Terawave as a defensive mode, a government-grade communications network reducing dependency on Starlink. More extreme theories imagine a shadow race for orbital weapons platforms disguised as data infrastructure. Control low Earth orbit and permanent lunar installations, and you influence more the markets. No missiles required, just systemic leverage. These claims are unconfirmed and speculative, but they persist because the trajectory shows rapid expansion, limited oversight, and growing concentration of orbital power. When private entities control infrastructure that nations depend on, the line between corporate strategy and national security blurs. And when two rival billionaires command expanding orbital fleets, the question shifts from market share to governance. Who decides what orbit looks like after the next crisis? Viewed through that lens, the debris problem changes meaning. If conflict, commercial or otherwise, escalated in orbit, debris would be both weapon and consequence. Deliberate collisions could render entire altitude bands unusable. Here is the darker edge of the speculation. If one operator has redundancy and high bandwidth resilience, and another holds numerical dominance, who benefits from a debris cascade that forces smaller actors out? Some corners of the internet suggest the answer is whoever anticipated it. That is not presented as fact. It is the logical extreme of unregulated expansion combined with rivalry and weak enforcement. Regardless of conspiracy narratives, measurable trends remain. Orbital objects are increasing. Collision avoidance capability is concentrating. And the relationship between the two most powerful figures in commercial space has shifted from open hostility to guarded competition. The tortoise and the hare metaphor is charming. But in orbital mechanics, neither wins if the track itself is destroyed. Active debris removal is technically complex, legally sensitive, and expensive. Under international law, space objects remain the responsibility of their launching state. Interfering with another actor's satellite, even if inactive, raises legal and security concerns. Liability is unclear. Jurisdiction overlaps. Governments therefore face significant barriers to direct action. Private operators operate under different constraints. They already maneuver satellites daily, track objects precisely, and maintain continuous control systems. They also possess launch capacity and on-orbit servicing expertise. As congestion increases, inaction becomes costly. Insurance premiums rise. Collision avoidance consumes fuel. Satellite lifetimes shorten. Launch planning becomes more constrained. Eventually, mitigation alone is insufficient. At that point, governments focus less on attribution and more on capability. Who can act quickly? Who already has assets in orbit? Who can operate continuously? The same companies that deployed large constellations are well positioned to meet those requirements. This does not imply intent to create a crisis, but it does mean that strategic advantage has been established. Once cleanup becomes unavoidable, it becomes a service, and services are contracted. That raises a legitimate policy question. If public authorities pay private companies to correct orbital congestion, is that accountability, or is it compensation for a predictable outcome of commercial expansion? Not all orbits behave the same way. Most current congestion occurs in low Earth orbit, roughly between 300 and 1,200 kilometers in altitude. These ranges are favored because they support efficient communication and observation. Atmospheric drag causes some satellites to re-enter over time. However, this process can take many years. During that period, those satellites remain collision risks. Fragments generated by collisions often persist even longer. They lack propulsion and cannot be actively removed without intervention. Guidelines exist. Operators are encouraged to deorbit satellites at end of life and prevent explosions. However, many of these measures are voluntary and weakly enforced. These frameworks were developed when satellite numbers were much lower. They assume cooperation and relatively low congestion. Once density crosses a certain threshold, prevention alone cannot reduce risk. Existing debris remains, and avoidance maneuvers increase system complexity. This is why current governance structures are insufficient for present conditions. If current trends continue, the outcome is gradual degradation rather than sudden failure. Launch insurance becomes more expensive or unavailable. Some missions are delayed or canceled. Operational costs rise. Satellite performance degrades unevenly. Navigation accuracy declines. Weather forecasting loses resolution. Communications experience intermittent disruptions. Access to orbit becomes increasingly unequal. Large states and corporations can afford advanced tracking and redundancy. Smaller actors cannot. Human spaceflight faces higher operational risk. Avoidance maneuvers become more frequent. Fuel margins shrink. Mission lifetimes shorten. None of this requires a catastrophic event. It only requires continued growth without coordinated intervention. As conditions worsen, the number of actors capable of operating safely declines. That scarcity increases the value of existing operators, which leads to consolidation. The space debris problem was not hidden, and it was not misunderstood. Scientific warnings were clear. Engineering analyses were public. The risks of scale were known. Expansion continued because accepting those risks aligned with commercial incentives. Early dominance created dependency. Dependency reduced regulatory pressure. Congestion increased the strategic value of those already in orbit. This did not require a conspiracy. It required incentives that rewarded speed and scale. Large constellations did not aim to damage orbit, but they did accept outcomes that made access more difficult for others. As congestion increases, cleanup becomes unavoidable, and cleanup becomes a service. When private actors control both infrastructure and remediation, public oversight weakens by default. Urgency replaces deliberation. This is not an argument against innovation. It is an argument for recognizing how incentives shape outcomes. Orbit is a shared and limited resource. Delaying governance concentrates power among those already present. The remaining question is not whether orbit can be cleaned. It is who will decide how it happens, who performs it, and who pays for it. And if you want to keep following stories like this as they evolve, make sure you're subscribed, give the video a like, and turn on the notification bell so you don't miss future investigations. It doesn't cost anything, but it makes a real difference for the channel. Sharing the video with someone who loves science, space, or skepticism also helps more than you might think. Because future struggles over power will not be limited to the ground or the internet. They will increasingly involve space.